This is video number 5 for week 8. So recall that a sequence xn is said to converge. Sequence xn is said to converge to a real number x if for every epsilon bigger than 0, one can find a natural number, capital N epsilon, such that the distance between xn and x is less than epsilon, okay, whenever small n is bigger or equal to capital N epsilon. Okay, now from the definition of the convergence of a sequence, we see that a sequence xn, okay, does not converge to a real number x, okay, if we can find at least some epsilon, at least one epsilon 0 bigger than 0. If we can find at least one epsilon 0 bigger than 0, such that for every natural number capital N, okay, there exists at least one natural number small n bigger than that natural number capital N. You will find at least one natural number small n bigger than capital N, right? Such that the distance between xn and x is bigger or equal to epsilon 0. Okay? We say that a sequence xn is divergent, okay, if it does not converge to any real number x. So if a sequence does not converge to any real number x, then we say it diverges. Now, there are different types of divergent sequences, okay. I'll give you a few types here, okay. One example of a divergent sequence is a sequence which alternates or oscillates between two different points. For example, the sequence minus 1 to the power n oscillates between minus 1 and 1. So that sequence does not converge. Another type of sequence which does not converge is one which tends to plus infinity. For example, the sequence xn is equal to n. Okay, sequence where a sequence where every term xn is equal to n. That sequence tends to plus infinity. The other sequence which diverges is, for example, the sequence which tends to minus infinity. As an example, if we take xn is equal to minus n for every natural number n, then that sequence tends to minus infinity. So it also diverges. Now, a sequence like minus 1 to the power n times n does not oscillate between any 2 points. It does not tend to plus infinity and does not tend to minus infinity. Okay, so this is also another type of sequence which diverges, but does not tend to plus infinity, does not tend to minus infinity, and does not oscillate between any 2 points. We now give a definition of a properly divergent sequence. Okay, now let xn be a sequence of real numbers. Okay, we say that 1, the sequence xn tends to plus infinity, and we write that the limit as n goes to infinity of xn is equal to plus infinity if for every real number alpha that you pick, okay, you will always find a natural number n that depends on alpha, such that if small n is a natural number bigger or equal to n alpha, then xn will be bigger than alpha. Take, for example, the sequence. Let me just illustrate this point here. Take, for example, the sequence n, okay, and pick n alpha in R, okay, pick n alpha in R, all right, pick any real number alpha, right? So this is our sequence n here. So xn is equal to n. All right. Now, if you pick any real number alpha, then the Archimedean property tells you that there exists some natural number n alpha, okay, such that n alpha is bigger than alpha. All right. So then you see, if you pick small n, bigger than your n alpha, right? Then that means that that small n will be bigger than alpha. Okay. So this sequence tends to sequence n tends to plus infinity. For the second part, we say that a sequence xn, okay, tends to minus infinity, and we write limit as n goes to infinity, xn is equal to minus infinity. If for every real number beta, there exists a natural number m beta, m depends on beta, such that if small n is a natural number bigger or equal to m beta, then xn will be less than beta. So if this happens, then we say that the sequence xn tends to minus infinity, and we write that the limit as n goes to infinity of xn is equal to minus infinity. Now, we say that a sequence xn is properly divergent if it either tends to plus infinity or it tends to minus infinity. Okay, so we will say that a sequence xn is properly divergent if it either tends to plus infinity or it tends to minus infinity. That is, if either the limit as n goes to infinity of xn is equal to plus infinity, or the limit as n goes to infinity of xn is equal to minus infinity. So let's look at some examples. The first example, we show that the limit as n goes to infinity of n squared is equal to plus infinity. So what do we need to do here? We need to show that if alpha is any real number, okay, that if alpha is any real number, then there exists some natural number, call it n alpha, okay, such that if small n is bigger or equal to n alpha, right, then xn will be bigger than alpha. But what is xn? Xn is square. Xn is n square. So we want to show that if small n is bigger or equal to n alpha, then n square is bigger than alpha. So that's what we want to do. So let alpha be a real number. Then the Archimedean property implies that there is some natural number n alpha such that n alpha is bigger than alpha, right? So if small n is bigger than n alpha, then for sure we have that n square is bigger than n, okay? But n is bigger than n alpha, okay? Now we can allow equality here. Can allow equality there. So we see that n square is bigger than n, and n is bigger or equal to n alpha, but n alpha is bigger than alpha, and therefore n square is bigger than alpha. So that's what you are doing here. So if n is bigger or equal to n alpha, then you have that n square is bigger than n is bigger than alpha, right? And so xn is bigger than alpha so long as small n is bigger than n alpha, and therefore the limit as n goes to infinity of n square is plus infinity. For the second example, we are given a constant c bigger than 1, and we are supposed to show that limit as n goes to infinity of c to the power n is equal to plus infinity. Please note that this one is c to the power n, not c square. So please replace this 2 by n. Okay, so we have to show that the limit as n goes to infinity of c to the power n is plus infinity. Now, since c is bigger than 1, right, then c can be written as c is equal to 1 plus b for some constant b bigger than 0. So if alpha is any real number, then the Archimedean property tells me that there is some constant n alpha and there is some natural number n alpha such that n alpha is bigger than alpha divided by b. And so if small n is bigger or equal to n alpha, okay, if small n is bigger or equal to n alpha, then we see that c to the power n, okay, which is simply 1 plus b to the power n, right, okay, is bigger or equal to 1 plus n times b. Here we are employing Bunless inequality here. This simply arises from Bunless inequality, right? And then, since small n is bigger or equal to capital N, then small n times b is bigger or equal to b times n alpha. So the constant 1 plus n small n times b is bigger or equal to the constant 1 plus b times n alpha. Now, I have that n alpha is bigger than alpha divided by b, and therefore this, if I replace n alpha by alpha divided by b, then the constant that I get here is smaller than the constant that I have here, right? But this constant here is simply 1 plus alpha, right? Because this simplifies to alpha. And 1 plus alpha is bigger than alpha. So replace this equal sign with bigger than. So what have we obtained? We have obtained that if small n is bigger or equal to n alpha, right? If small n is bigger or equal to n alpha, then c to the power n is bigger than alpha. Okay? In other words, xn will be bigger than alpha. So then we conclude that limit as n goes to infinity. We conclude that limit as n goes to infinity of c to the power n is equal to plus infinity. Again, replace this by c to the power n. Replace this 2 by n. So the conclusion from here, okay, is that right, is that the limit as n goes to infinity of c to the power n is plus infinity.